Welcome to The Explainer. Today, we're diving headfirst into a concept that literally places a fundamental limit on what we can ever know about the universe. Seriously, it's a rule that shatters our everyday intuition and shows us a cosmos that is way, way stranger than we ever thought possible. So, let's start with what seems like a really simple question. Imagine an electron, just one tiny particle. Can we know its exact location and its exact momentum, where it is and how it's moving, at the very same instant? I mean, it feels like we should be able to, right? But the laws of quantum mechanics are absolutely clear on this. The answer is a hard no. It is fundamentally completely impossible. And let's be super clear about this. This isn't because our measuring tools aren't good enough. Nope. Even if you had a perfect godlike instrument, you still couldn't do it. This isn't a tech problem we're going to solve one day. It's a core rule that's woven into the very fabric of reality. Okay, so why? What is actually stopping us? Well, let's begin with the classic explanation, the one that kind of gives you a first glimpse into the problem. It's a really helpful way to start, but you've got to stick with me because the real reason is even more mind-bending. Think about it like this. To find a book in a totally dark room, what do? You turn on a light. Photons, particles of light, have to shoot out, bounce off the book, and then hit your eyes. That interaction is what lets you measure where the book is. The same basic idea is true at the quantum level. This brings us to what's called the observer effect. To see a tiny little electron, you have to hit it with something, and that something is usually a photon. But an electron is so incredibly small that getting hit by a photon is like a billiard ball getting slammed by another billiard ball. The collision gives you the location, sure, but it also sends the electron flying off in a new direction. The very act of looking at it has completely changed its momentum. So you're stuck in this unavoidable trade-off. If you want a really sharp, crystal clear picture of the electron's position, you have to hit it with a high-energy photon. But that photon hits like a truck, making the momentum a total mystery. So, okay, what if you use a really gentle, low-energy photon? Well, that won't mess with the momentum much, but because it has a long wavelength, it gives you a super blurry, fuzzy idea of where the electron actually is. You can know one thing precisely, but only if you're okay with the other thing becoming a total blur. Now, that whole observer effect thing, it's a fantastic mental picture. It's even how Heisenberg himself first tried to explain the idea. But, and this is so important, it's just a helpful analogy. The real reason for uncertainty isn't about us being clumsy observers. The truth is much deeper, and it's built into the very nature of what a particle is. All right, let's get to the real heart of the matter. And to do that, we have to totally rewire our brains about what a particle even is in the first place. This is where things get really, really weird. We're used to thinking of an electron as a tiny little ball, right? A solid dot with a specific location. But quantum mechanics tells us that's just plain wrong. Before we measure it, a particle isn't a dot at all. It's a wave of probability. It's a smear of potential locations and potential speeds all existing at once. Back in 1927, the genius German physicist Werner Heisenberg captured this bizarre truth about nature in this one elegant equation. This is basically a mathematical guarantee from the universe itself. It says that the uncertainty in position, that's the delta x, multiplied by the uncertainty in momentum, delta p, can never ever be zero. There is always a baseline level of fundamental fuzziness. Now, this quantum wave isn't like a wave in the ocean. It's a purely mathematical thing called the wave function. The best way to think about it is like a cloud of possibility. Where the cloud is thickest, there's a really high chance of finding the particle if you look for it. Where the cloud is thin, the chance is much lower. So what happens when we finally do decide to measure it? The instant we interact with that particle, the entire wave of probability instantly collapses down to a single point. And this is the crazy part. The particle wasn't hiding in that one spot the whole time. It genuinely did not have a precise location until the moment we looked. The act of observation literally forces reality to pick one outcome from an ocean of possibilities. This idea that reality is fundamentally fuzzy and undecided until we interact with it, well, it has some absolutely massive implications for how we see the universe. What it means is that the old dream of a clockwork universe is dead. The idea that if you just knew the position and speed of every particle, you could predict the entire future with perfect accuracy. The uncertainty principle tells us we can never know that initial information perfectly. The universe, at its most fundamental level, doesn't run on certainty. It runs on probability and chance. Now, this whole idea of a random, probabilistic universe really bothered a lot of physicists, and the most famous was Albert Einstein. He was convinced that this uncertainty was just a sign that our theory was incomplete. He famously said this, arguing that there had to be some deeper, predictable reality that we just couldn't see yet. But his colleague, Niels Bohr, who was a key architect of quantum theory, had this legendary comeback. Bohr and his supporters basically said, we have to accept what the experiments are telling us. The universe is inherently uncertain, whether we like it or not. And you know what? For nearly a century, every single experiment has proven Bohr right. At this point, you might be thinking this is all just strange, abstract philosophy. But this principle isn't some weird theoretical quirk. It is the absolute bedrock of our entire modern technological world. Far from being a flaw, this uncertainty is a feature that we have learned to use. The behavior of semiconductors in every single computer and phone chip is governed by it. The incredibly precise light from lasers, the mind-boggling power of quantum computers, the unbreakable codes of quantum encryption, all of these technologies rely on the principles of quantum mechanics with uncertainty right at their core. So if you take one thing away from this, let it be this: the fuzziness, the probability, the uncertainty. It isn't a mistake. It's not a sign that our tools are clumsy or that we're ignorant. It is a real, baked-in property of how the universe actually works. And that leaves us with a pretty profound thought. Absolute, perfect knowledge about the physical world is literally impossible. There is a hard limit on what can be known. And in a way, that doesn't make the universe less interesting. It makes our quest to understand it even more amazing and wonderful.